Hello everybody, and welcome to the beginning of section 1.5. We are looking at page 23 in the workbook, and we are about to talk about another big definition in our linear algebra course, the idea of linear dependence and independence. And I think the best way to get started on this is just to consider an example. Okay, so let's read example 1 together here. They'd like us to consider four vectors, u1, u2, u3, and u4, in three-dimensional space. And they start us off with a fact, and that is that the span of these four vectors is all of R3. Okay, in other words, what we're saying is that if we take the right linear combination of those four vectors, we can build any vector in R3 that we want. Maybe just to give you a little graphical insight into this, I'm going to flip the pages here on you. Here's a picture of the four vectors u1, u2, u3, and u4. Okay, so you can imagine that just what we said previously, that you just kind of take an arbitrary vector in R3. If we combine these four vectors together, we can build that vector. That's what we're saying. Okay, so back to the page we were on, and here's the key question that we want to think about. Are all four of these vectors necessary in order to span R3? Or might it be possible to get rid of some of these four vectors and still have enough vectors to span R3? That's the question we want to answer. And I'd invite you to maybe pause the video for a minute here. Okay, pause the video and just ponder this question. What do you think the answer to this is? Okay, do we need all four of these vectors, or could we get by with fewer to span R3? Okay, so hopefully you gave this question a little bit of thought here. And this might have led you back to things that you learned in previous linear algebra courses. Like you might remember hearing something about R3 is a three-dimensional space, so maybe it's not necessary to have four vectors, something like that. Okay? Well, let's just pursue this a little bit. Okay, so if the answer to this question were no, in other words, if it was not necessary to have all four of the vectors, then it should be possible to write one of the vectors as a combination of the other three. Okay, one of the vectors as a linear combination. I'm going to use the abbreviation LC for linear combination. Okay, I hope you don't mind. All right, so for example, what that might mean is maybe we can write u1, let's say, as a linear combination of the other three vectors. So u1 is some constant a times u2 plus some constant b times u3 plus some constant c times u4. Okay, and what's interesting about a statement like that is that we can rearrange it. We can take that equation and get all of our vectors on one side so that the zero vector is on one side of our equation. So we could rewrite this like this. u1 minus au2 minus bu3 minus cu4 is equal to the zero vector. Okay, so one of the vectors depending on another vector is equivalent to kind of taking a linear combination of all four of our vectors and setting it equal to the zero vector. Okay, let's take that observation and pursue it a little bit further here. Okay, so part A says, let's begin with the vector equation kind of similar to the one that we have up here, where we take a linear combination of our four vectors and set it equal to the zero vector. Okay, now here we kind of think back to some of the previous work that we did in the previous section. When you want to solve a system of equations like this, what you get is, if you write it in matrix form, is a matrix where the columns of your matrix are these four vectors, u1, u2, u3, and u4. Okay, and then here's the zero vector on the right-hand side. That's making the same algebraic observation that we made in the last section. Okay, and we wanted to solve that system. We would do row reduction, and I went to a program like Mathematica to do this row reduction. We get a nice echelon form here, and I'm going to go ahead and circle the pivot positions. Okay, those are again the first non-zero entry in each row of our matrix. Okay, and then I'm going to go ahead and just write out the equations that are left over. So if we read those off, the first equation would read a1 plus 2a3 equals 0. We've got that 0 on the right-hand side. Okay, this second equation would look like a2 minus 3a3 equals 0. Okay, and then finally the last equation would just look like a4 equals 0. Okay, and what we want to do, okay, taking those observations and pulling them together, is to find the general solution of the system of equations above. Okay, and then let's just tackle that first sentence for. They're kind of asking us first. They're asking us a lot of things in part B. Okay, so the solution to that system of equations, we could start by asking ourselves, do we have any free variables? Notice that we do, because the third column doesn't have a pivot position in it. Okay, so we'll start with that observation. And since x3 is free, I'm going to just give it a variable name. We'll call it t. Okay, it can be anything. That's what it means to have a free variable. Okay, so t can be anything. And if we do that, now the question is, what are the other three variables, a1, a2, and a4, if we let a3 be t? Okay, well, we can figure that out by kind of looking back up at our equations, starting with this one. Okay, so we've got a1 equals, let's subtract 2a3 from both sides, and we let a3 be t, so we're just going to get negative 2t out of this. Okay, and then we'd move on to a2. We can get that by looking at our second equation up here. Okay, if we take that second equation and add 3a3 to both sides, we're going to get 3a3, which is 3t. Okay, and then finally, the last equation, nothing to do, it tells us directly that a4 is 0. Okay, I'm going to go ahead and, just for good measure here, write down what a3 was. Okay, that's sitting here. a3 is t, and then finally a4 is 0. Okay, that's our solution to the system of equations. Okay, now, next sentence says to find a non-trivial solution, okay, to this system of equations. What do we mean by that choice of words? Okay, well, we can start by reminding ourselves that t can have any value. It's a free variable. So what would happen if we let t be 0? If we let t be 0 for every equation in this line? Well, if you did that, every value would be 0, and we would get what's called a trivial solution. A trivial solution means that all of the variables have the value 0. Okay, so how would we get a non-trivial solution? Well, we just choose a value of t that's not 0. Okay, so how about t equals 1? Okay, letting t equal 1. We obtain the non-trivial solution. Okay, and all we're going to do is to just go back up to this line. Everywhere you see a t, we're going to put a 1. Okay, that's going to give us a1 equals negative 2 times 1 is negative 2. a2 is 3 times 1, that's 3. And then a3, that's just t, which is 1, and then a4 is 0. Okay. And that's a non-trivial solution because we look at those 4 values and they're not all 0. That's what we mean again when we say non-trivial. Okay, well, what does this all mean? Okay, well, let's think about it in the context of the system that we just solved. Okay, this indicates the following. Okay, so we're going to get, let's go back to our system. And remember, that takes us way back to here. Okay, we really just found the values of a1 through a4 for that system. So we're just going to substitute the values of a that we found one by one. So a1, that's negative 2. So we'll get negative 2u1. Then we come to a2, that's 3. Okay, and so on. Plus 1u3 plus 0u4 is equal to the 0 vector. Okay, and what's interesting about that equation is that we can take that equation and solve it for one of the vectors. Okay, what would be the easiest vector to solve for here? Probably u3 because it's got a 1 in front of us. Of it. So if we solve that equation for u3, just move everything to the other side, you're going to get a positive 2u1 minus 3u3, and then plus or minus doesn't matter, 0u4. Okay, so we've shown a very interesting thing here. We have shown that u3 depends on the other three vectors because we were able to write u3 as a linear combination of u1, u3, and u4. This is what's known as a dependence relation. Okay, so here comes the critical argument, okay, or the main point of this. u3 is a linear combination of u1, u2, and u4 and so going back to the very first question, okay, way at the beginning, are all four of the vectors necessary to span R3? We now know that the answer is no, because we can get the vector u3 as a combination of u1, u2, and u4. We don't need u3. We can already get it using the other three vectors. Okay, so we can complete this statement as follows. So it is unnecessary in the set u1, u2, u3, u4. Okay, another way to say that, I mean, what we mean by unnecessary, I'm going to kind of put that in quotes. It just means that if we take the span of just u1, u2, and u4, that's going to give us everything that we would get if we took the span of all four of the vectors. Okay. Now that's the end of this video, but some of the observations that we made here are going to lead us to the definition of linear dependence and independence, which is one of the most important concepts in our course.